Okay, today we are going to study some of the concrete continuous probability distributions. First of all, let us review uh, the density functions. Okay, let's say x, wait a minute, x is a continuous random variable. Random variable. Then we can usually assume the existence of a density function. Let's say this is density function such that the probability that this random variable takes a value between a and b is given by this integral. Okay, so usually we can assume that this kind of density function exists for any well-behaved random variables. Okay, so first we study a very simple distribution called uniform distribution. Let's say uh, if x can take any value between a and b, let's say, it could be both closed, both open, or semi-closed, so open to the left and closed to the right, or vice versa. But anyway, if there is an interval, and if this continuous random variable take any values between these a and b, then if the density function is given by this, of course b is supposed to be greater than a. Okay, if the density function is given by this formula, then we say this random variable x follows a uniform distribution between a and b. So we write x follows uniform. So let's suppose we use this definition. In this case, we write like this. Okay. So let's see some very simple example. Okay. So let's say if we have a uniform distribution between 0 and 1. Okay. In that case, the density function is 1 over 1 minus 0, so that's just 1. As long as x is between in this interval. Okay? Otherwise, the density is 0. Okay, very easy. And another example, let's say uniform distribution is between 0 and 0.1, okay, both exclusive. Then the density function is 0.1 minus 0, so that's actually 10 as long as x is between 0 and 0.1. Okay, so notice that this value is greater than 1, but that's okay because this is a density function, not the probability. Okay, So the probability is given by this integral. So as long as this integral remains below zero, below one, then this is okay. You know, from the first axiom of probability measure, this must be between 0 and 1. So if you integrate this and still have a value between 0 and 1, it's okay. So, for example, in this case, the probability, let's suppose this uniform distribution. And then the probability that this random variable x is between some numbers a and b, then it's given by this integral a and b and 10, which is just 10 times b and a. Okay, but we're assuming this value x is between between 0 and zero point 0.1. So 0, a is greater than 0 and less than b, and b is less than zero point 0.1. So we have to assume this relationship, this order. So that means b minus a here, that appears here, is always greater than 0 but less than 0 0.1. Okay, so that means 0 times b minus a is less than 1. So this is okay. It can satisfy the axiom 1 of the probability measure. Okay, and of course it satisfies other axioms. Okay, so here's one quiz which can be difficult. Let's consider a uniform distribution. Between 0 and 1. Okay. Now, this interval between 0 and 1 can be, it seems that it can be expressed as a union of all values between this interval 0 and 1 and single points. Okay, this, for example, 0 0.1 is a subset of this interval, right? This subset consists of only 1 point, 0 0.1. So if you just enumerate, if it's possible, all the values between 0 and 1 and take the union of all these subsets, single point subsets, singleton subsets, then it seems we can recover this interval. Okay, and of course each of these subsets are disjoint. Uh, uh, Subset is disjoint from other subsets, single point subsets, because there are no 2 points that are identical. Okay, so that means if x and y are different, then if you take this intersection, it's empty set if x is not equal to y. So it seems probability of this interval is just the probability of union of this. So according to axiom 3 of probability measures, then we may split this probability into summation of probabilities. But the probability of a single point in continuous distribution is zero. Why? Because according to if we use the uh, density function, this is like x integral from x to x of density function. Let's write x prime here. So that's always zero, right? So each term in this summation is zero. So if you add all the zeros, then the result is zero. However, if we just directly calculate this probability, this is equal to 0, x less than 1. So that's 0 to 1, and the density is 1. So it's 1, which is not 0, of course. So this is a contradiction. What was wrong with this argument? Think about this. And I'm not telling you the answer. Okay, now let me explain beta distribution. Okay, beta distribution is defined by this density function. Okay, alpha minus 1, 1 minus x, beta minus 1, and b alpha beta. Okay, this alpha and beta, they are parameters of beta distribution, and they have to be positive. Okay, and this function in the denominator is there. It's a constant. It's called the beta function. Okay, this is here just to make this probability distribution normalized. Okay, that means if we integrate, okay, I have to say this x varies between 0 and 1. Okay, maybe we can include equal sign here, but okay, so x varies between 0 and 1, and alpha and beta are parameters that are positive. And if we integrate this integral, density function, from 0 to 1, then that is equal to 1. So this is how we define this beta function. Okay. Then if x is a random variable that follows beta distribution, we write beta, alpha, beta. Okay. So depending on the values of alpha and beta, this function, density function, looks very different. Okay, here are examples. And this figure was taken from Wikipedia, so you can look at this figure here. And when alpha and beta are 0.5, we have this curve. Okay, so that means the density is higher when x is close to 0 or close to 1. Okay, and it has the minimum value at x is equal to 0.5. Okay, and when alpha is 5 and beta is 1, so alpha is larger than beta, in that case we have this curve. Okay, so when x is close to 0, then the density is 0, close to 0. And when x is close to 1, then the density is very large. Okay. If you look at these values, it can be greater than 1. Okay. But still, if you integrate this function, the value of the integral is always less than or equal to 1. Okay? And if you have a value, let's say alpha is 2 and beta is 5, then we have uh, this function. So in this case, when x is close to 0 or close to 1, the density is small, close to 0. But somewhere around x equal to zero point 0.2 or so, the density takes the largest value. So this beta distribution is very handy if you want to model something that takes value between 0 and 1. So by adjusting the values of alpha and beta, you can model many types of distributions. Okay, so for example, when alpha and beta are both 2, then it's a symmetric distribution around 0.5. Okay, this one. Okay. So if beta is larger, it's shifted towards to 0, and if alpha is higher, then it's shifted towards uh, higher value of x. Yeah. And that is beta distribution. And you should try to find the expectation value and the variance of this distribution. Just apply the definition. Now let's study a little bit more about the beta function that we found in the density function of the beta distribution. So in that density function, let's write it again. We had x alpha minus 1, 1 minus x beta minus 1, and here's the beta function. Okay, since the density function, when integrated over all the range of the random variable, that is from 0 to 1, it must be 1, right? So if you substitute this density function here, then we have x alpha 1 minus x beta 1 beta alpha beta dx. Okay, but this is constant, so we can put this out of the integral, and x alpha minus 1 minus beta minus 1 dx, which is equal to 1, right? So from this, we can see that this beta function is actually defined by this equation, this integral. So x alpha minus 1 minus x beta minus 1. So you can consider this as the definition of the beta function. But it has an interesting relationship with another function called gamma function. And the definition of the gamma function is this. So gamma function, we write gamma z. Actually, this z is a complex number, okay, in general. Sorry, this is integral from 0 to infinity, and x to the power of z minus 1 exponential of minus x and dx. Here, this z, the variable here, is actually a complex number. So complex number. But not any complex number, but its real part. So real part of this z must be greater than 0. Okay? Any complex number can be written like x plus iy, where both x and y are real. So in this case, real part of z is x, which must be greater than 0. So for such a complex number, this gamma function can be defined. Okay. And this integration is for this real number from 0 to infinity. Okay. You should try to calculate these values, gamma 1, gamma 2. Okay, what do you find? And actually there is an interesting recursive equation for this gamma function. That is gamma z plus 1 is equal to z times gamma of z. Okay. So this is a kind of recursive equation. And in particular, when this z is a natural number, okay, then we have, because of this, if we have a natural number, then this is actually n minus 1 factorial. Yeah, you can derive this from the definition. And maybe you want to use mathematical induction to prove this. Okay. And there's a relationship between this gamma function and the beta function. That is beta alpha beta is equal to gamma of alpha times gamma of beta over gamma of alpha plus beta. Okay. Can you prove this? And also, because of this relationship result, when alpha and beta are natural numbers, okay, then we have 1 over beta function of alpha beta is equal to alpha plus beta minus 1 factorial and alpha minus 1 factorial and beta minus 1 factorial. Okay, this almost looks like like combination, almost like alpha plus beta choose alpha or something like that, but a little bit different. Okay, so if you use this formula for natural numbers alpha and beta, then you can rewrite the density function of the beta distribution as this. So that's alpha plus beta minus 1 factorial, alpha minus 1 factorial, beta minus 1 factorial, and x alpha minus 1, 1 minus x beta minus 1. Okay, and alpha and beta are natural numbers, and x is between 0 and 1. Okay, but doesn't this look familiar a little bit? Do you remember the probability mass function for the binomial distribution? It looked like this. Something like n k n minus k factorial p k and 1 minus p n minus k. So this is binomial distribution. So that's b and p, right? So this part looks similar to this part, and this part looks similar to this part, and this part looks similar to this part, right? And actually this similarity uh, turns out to be very convenient when we deal with Bayesian inference that we will study in a later chapter.